I thought we were expecting a big crowd tonight. Can we try that again? Bit more. Come on. Can you, hands up the back if you can hear me. Oh, not everybody. Let me give that some more volume. 1, 2, 1, 2. 2, 2, 2. Uh-oh. I'm breaking up. There we go. That's a bit more like it, isn't it? How about this speaker? Yes. All right, my speakers have been in retirement over the lockdowns, and they're so happy to be out again, but they've forgotten a little bit about how to work. But anyway, thank you so much for coming out, everybody. The first thing I'd like to do is acknowledge the traditional owners of the land, the Gadigal people of the Eora Nation. Big shout out for them, hooray! We acknowledge their leaders, past, present, and welcome any Indigenous people who are here tonight. My name's Dr Phil Dooley, and under the banner of Fill Up on Science, I do all kinds of things, which include pub nights like this. And I'm very, very pleased to have partnered with the Australian Institute of Physics, New South Wales branch, and to be sponsored by Laboratories Credit Union for this evening's festivities. So thank you very much. And we've got a great lineup of people here who are going to share their amazing science. So where do we begin? The first thing that you need to do as a science communicator is to understand your audience. Isn't that so, presenters? Yes, they're all very interested in understanding you. So what I would like you all to do is put your hand up if you went to primary school. Yes, excellent. All right, leave them up there until we reach, did you go to high school? Did you go to year 11 and 12? Who did science in year 11 and 12? Who went to university and did science and did physics? Ooh, that's thinned it down a bit, hasn't it? Physics first year, second year, third year, honours, masters. Oh, we lost a few there. Professors. Yes, a couple of professors there. Are you? Congratulations. Associate professors. I forgot associate professors. Look, they're professors as well. I'm happy with that. Any Nobel Prize winners? Yes, we've got one up the back. Congratulations, sir. It has happened once. So I always keep testing the waters. Any people who are going to win a Nobel Prize in the future? Yes, excellent. Some of those are the people who didn't even go to high school. And that's the kind of thinking it takes. Anyway, so there you go, presenters. You know all about your audience now. We've got a mix of people. We're going to have some heavy-duty science. We're going to have some light-hearted stuff. And I hope somewhere along the way there's something that floats your boat. That's buoyancy, first-year physics. And we are going to now... audience, you have to do something for the presenters. They know about you, but now you need to know that we have real live scientists who've come down from their ivory towers, and they are in a public space, interacting with alcohol. What could possibly go wrong? They might meet normal people tonight. Are there any normal people in the room? You're all individuals. Thank you. Thank you. Good to see the faithful are still here. So, what might happen? I'm just warning you, is that there might be a joke, a science joke, Hey? And what do you do if that happens? You can try that if you like. But a few angry scientists will be pursuing you around and going to do experiments on you if you try that. If someone tells you a science joke, what do? No, you don't cheer. It's a joke. Oh my God, let me try it out on you. Well, I was trying to decide which joke to use today. I was thinking about maybe a statistics joke, but they're all a bit average. No booze. No booze. You were up here last year, buddy. You were up here. Oh boy, you're blacklisted. All right. Did you hear about the perverted statistician? Really perverted. Standard deviation was not enough. A bit more. Standard deviation was not enough. Hey, that's better. If they tell you something that really blows your mind, you go, ooh. That's good. And if they tell you something you completely don't understand, you just go, whoa. That's good. And maybe another science joke. I was going to tell one about the periodic table, but all the good ones are gone. Now you've forgotten already. All the good ones are gone. No, don't cheer. Oh my God, you're slow learners here. All right, look, I think you'll get the hang as we go along. It's getting close to know. The last thing I would quickly like to do a quick survey and find out where you heard about this. Who got an email from the Institute of Physics? Who got an email from me? Who got an email from a friend or a presenter? Who's been dragged along by a friend tonight? Who thought it was trivia about wombats? 3, again, nice. Who saw a poster? Good, we didn't put any up. Who saw it on Twitter? Oh, every time. Instagram, Facebook. All right. Who? Yeah. There's a whole lot of people who haven't put their hands up. Anyway, that's enough from me. I think we should get on with it. Is there anything that I haven't asked? Who saw it on the National Science Week website? Ah, that's good. That's good. Welcome. All right, so what we'll do now is just stop for a quick word from our sponsors. Fred, where are you? Fred Osman from the Institute of Physics. Big round of applause for Fred Osman.
Thank you, Phil, and it's great to be back. After 2 years in lockdown and online, Physics in the Pub is getting stronger than ever. And just want to say thank you very much for coming out to the Harold Park Hotel. The management's been wonderful here. The hotel staff looked after us. I'd like to thank all our presenters. This couldn't have happened without our presenters. And also Phil Dooley running the show. And also a big, big thanks to LCU, Laboratories Credit Union, for being part of our main sponsor for this event. So thank you very much for everyone for coming. I want you to have a great time tonight. Enjoy it. Stay connected, and most importantly, stay safe. Thanks.
You forgot to say AIP.org.au, and it's very cheap as a student to join up. But he mentioned Laboratories Credit Union, and who might LCU be? Laboratories Credit Union was founded in 1954 by CSIRO staff members. So they're like real sciencey people. Provide affordable credit and a better banking experience for scientists. Who wants a better banking experience, huh? These days, they provide service for members of the STEM industry throughout Australia, as well as their family and friends. When you call LCU, you will always speak to a person. That's not what scientists want, is it? Not a call generator, not a call center or an automated phone system. They give their members not only great personal service, but also a one-call service outcome. There you go. No ringing back. Whether it's over the phone or in the branch, members love the personal service. Most of the business comes from referrals. LCU offers banking products including savings, transaction accounts, as well as mortgages. And the mortgage application process is so simple. You will have direct access to the creditor assessor to discuss your loan. Who knew you could actually talk to the person who's assessing your loan? That's amazing. Unlimited extra repayments, 100% offset account, no ongoing fees. Check the LCU website, and they'd be so happy to talk to you if you call them. So, big round of applause for LCU. All right, enough blithering on. Oh, the computer's gone to sleep. Oh.
Hey, thank you. Hey, I'm actually going to use this. Yes, actually the best warm-up I find is squats. Highly recommended if anyone's looking for a tip. Right, so I was going to start off with some jokes. I already have, but I'll keep going. These were the ones I was saving for later, but you know what? You're so great. You're so wonderful. We're going to do them right now. It's not because of anything that's happening behind me. What do you do with an angry astronaut? You give him space. Yeah, Lesley, you're right. The cheering's good. I'll take the cheers. All right, the next one is how do you organize a space party? You plan it. Yes. Oh, so I know a lot of people call them dad jokes, but I'm not going to be a dad anytime soon. So we could call them daggy jokes, but I feel that's offensive to sheep, and the Americans don't know what to do with that word. So I was just going to call them jokes. Yeah? Yeah, right? I think that's great. And do you know what? I discovered recently that joke is a really old word. It actually has a Proto-Indo-European root of yokos, which means word or utterance. So then that became like word play throughout time, which means that we have a similar word in lots of languages, in Germanic and Scandinavian and Romantic languages, but we can't say that, of course, for all our words. For example, ambulance is ambulance, ambulance, and Krankenwagen. So yes, but I digress. What I did want to talk to you today about, fiddling with all the things, if I keep talking, yes. What I did want to talk to you today is about something that's much heavier. Oh, actually, no, I should introduce myself first. I'll introduce myself first. I am Rachel. My name is Rachel. I've got a science show happening at Sydney Fringe very soon. It's a science comedy show called A Flying Photon, and it's just about the quantum mechanics of the electromagnetic spectrum, right? So it's really just an evening of enlightening light entertainment. Yeah. Assessing the audience. So since that I've got this show all about light, I thought I'd bring you something much heavier today, something much heavier material, which is, of course, something I think that's been weighing on all of us recently, which is the fragile state of our crumbling democracy. But thank you, Morrison, for pointing out how fragile it was so elaborately. Yes? Don't worry. I know it's a science gig, and we're here for the physics, so I thought I'd talk about gravity, right? Because it really is quite a heavy topic, yes? But I find it really just draws you in, yeah? Yeah, it can really weigh us down, but in the end, it just keeps us grounded, right? And also I think gravity has something that perhaps my puns don't have, which is mass appeal. Don't worry, I've got so many more gravity puns, but I think I'll just drop them. But gravity is really quite complex. I don't think we appreciate how complex it is. It can really just trip us up so quickly. Yeah, I'm going to leave the puns, I think. Yes, lots of nodding at the back there. Yeah. But the reason gravity is so complex is because we've been lied to our entire lives. Many of us have been lied to as children. Who's ever been told that astronauts float because there's no gravity in space? Yeah? Yeah? Right? Yeah, that was a lie. Yeah, it was a lie. Yeah, in the education business, this is called lies to children. Yeah, there's quite a few of them, actually. But the astronauts floating in space, I think, is a good one, because when we're younger, we just get told that they're floating because there's zero gravity up there, and you just kind of leave it at that. Then you get a little bit older, and then it's like, well, no, actually, the astronauts are in microgravity. And then at one point, you're old enough, and you're ready to know the truth. Some of you may not be there yet, but I'm going to take you with me today, and I'm going to reveal the truth. I'm sorry, but yeah, apologies in advance. Astronauts float because they're free-falling around the Earth. Like a lift with its cables cut, they are just falling. They just happen to miss the Earth. They just keep missing the ground. So astronauts are actually under the same amount of gravity that we are right now. They're in free fall. Right, I know. When we get through these lies to children that we've been fed all our lives, don't get me started on the atom, then there's really some wonderful, magical things around us. So I think it's amazing. And the more I look into quantum mechanics and subatomic physics, the more wonder I keep discovering. Like, for example, metal feels cold to the touch, right? Yeah. But metal is the same temperature as everything else around it. If it was colder, it'd be breaking the laws of thermodynamics, right? Metal feels cold to the touch because it's taking the heat away from you. You're the cold thing. Which reminds me about this boyfriend I once had. And he used to think that no one could be a fully fledged human unless they'd done psychedelics, because if you do psychedelics, you can see deep into the world. And I was like, mate, I've got quantum mechanics. You want to see deep into the world? Oh my goodness me. What it means is that I know that if I see static on TV or if I hear it on the radio, I'm picking up the earliest light in the universe, cosmic background radiation. Whoa. You think your last drug-induced trip was impressive? I've got string theory. We're all vibrations, man. Oh my gosh, so good. Who knew that maths was the real gateway drug to weird realities, huh? Anyway. So, funny enough, he was someone that really mattered to me at some point, but then I kept studying atoms more and found out that he was mostly nothing. Yeah, the universe is brutal. Yes. But anyway, I'm going to end tonight. How are we going? Great, obviously. Oh, great. So I'm going to end this evening on an experiment. Not a drug one, you're good. Because I think it's just fun to do something. So, yeah, Phil, I will get you up for some help. Yep, you get those two, and I'll start with the banana. Yeah, so I thought I'd drop some more truth bombs. It's a gravity show. And yes, so the fun thing about gravity, when we drop things, they fall, right? Yes, right? Yeah, you can drop the banana. Ah, well, you wouldn't let me drop the microphone, and an apple had been done before, and it rolls. So, drop the banana. Now, what I love about that is we know exactly how... Bonus gift? Thank you. We know exactly how fast the banana fell. It was 9.98 meters per second, right? Very cool. But I have two things here. Oh, I know we're at a little slightly different point of the Earth rotate. It's slightly different here for spherical physics, spherical globe. So I've got two bottles here. Now, does how they fall change with mass? That's the question. And I'm going to ask you guys, I'm going to give you three options. So what's going to happen when Phil drops these bottles? So, thank you, I'll just take this. So we've got one that's empty, and we've got one that's... No, it's fine. And one that's full of water. All right, so you've got three options. One, is the heavier one going to hit the ground at the same time? Is the heavier one going to hit the ground first? That's A, all right. B, will they both hit the ground at the same time? Or C, are they actually quantum entangled and they're going to end up in an undisclosed location? C? All right, no. Okay, who's up for A? The heavier one will hit the ground first. Yep. B, they're going to hit the ground at the same time. A few more for that. And C, they're quantumly entangled. Yes. Of course, I'm a magician. All right, so... If you'd like to take your place, Phil, please hold them out in front. I'm going to make sure they're evenly aligned. All right, I think that looks pretty good. Okay, we're going to Phil's going to drop them on a countdown from 3, all together now. 3, 2, 1. They were meant to hit the ground at the same time.
They did with an experimental error.
Yeah, that's true. Standard deviation.
I'm a physicist.
Well, actually, so they do. It's when you ask a mansplainer what a body of water is. Well, actually. I like that joke.
I like it.
So Aristotle predicted that heavier things would hit the ground first. It was another 2,000 years before anyone bothered to actually try the experiment, right? And that was Galileo who discovered that things will all hit the ground at the same time. It's not their mass. Their mass does not change the speed of which they fall. It changes the force with which they fall, but not their speed. Yes, so think that was, I was going to say something else from that. Yes, so keep looking at the world, keep asking questions, and keep experimenting. It's not enough just to think about something. It's worth doing a test too. But I'll leave you with this final thought. I think we can all agree it's very expensive living in Sydney right now, yes? And thank you for putting on a free event. Fantastic. Round of applause for everyone at AIP and Dr. Phil Dooley and our sponsors, LCU. And yes, so even though it's quite expensive, just remember that every year we still get a free trip around the sun. Thank you, Gravity. Thank you, audience. You've been fantastic, and enjoy the rest of the evening.
Rachel Rader! Did you notice she didn't do any of the anti-gravity jokes? Because she knew they wouldn't land. That's the advantage I have. I knew what she was going to talk about. All right, we are going to give up on the screen for the moment and go for those amazing individuals who don't even need visuals. So we're going to jump to shortly, John, if you're anywhere around. Oh, there you are. Good. Not yet. We'll go for Greg Pitt first. Over to you, Greg Pitt. All right, I'm going to get you a stand to use. You could, that would be great, John. And John's helping as well. It's just all happening around here. All right, I'm trying to think of more maths jokes. There is a physicist, an engineer, and a mathematician staying in a hotel. And they all went to bed. They had a big night drinking, as those scientists are wont to do. They all went to bed. In the middle of the night, the physicist woke up smelling smoke. He ran out into the hallway, and there was a cigarette butt smouldering in a bin. And he looked at how big the cigarette butt was and the paper that was smouldering, and he worked out exactly the right amount of water to put it out. Went and got that water, poured it onto the thing, put it out. Hurrah. Disaster averted. An hour later, who would have believed it? Somebody else chucks a smouldering cigarette butt outside the engineer's room. And he runs out, or she runs out and sees the smouldering thing looks at it and goes, okay, it's this big. I'm going to get as much possible water as I can and absolutely slosh it and completely wipe it out. Just completely overkill. That's the engineering approach. I've told it wrong. I panicked under pressure. I'm going to get back to you on that one. I've given away the punchline. Anyway. The mathematician wakes up. I'm going to adjust it. The mathematician wakes up, looks outside, and there's a piece of paper and a dead cigarette butt. And thinks, oh, there's a problem. So lights the cigarette butt, gets it smouldering, puts it into the paper, and then goes to bed happy. It's been reduced to a previously solved problem. Over to you, Greg. Do better than me.
Thank you, Phil. I'm really terrified because I didn't know I was supposed to be funny. But I probably will be unintentionally, so just forgive me for that. Hi, it's really great to have you here tonight. I've been interested in physics since the steady state theory was a thing. I'm Greg, and I'm here to talk about predicting the future. But before I start, get into the real meat of it, here's a real story. A friend of mine rang me about a week ago. He's about the same age as me, so that sort of sets the scene. And he said that his ophthalmologist had told him that he would be blind in 6 years. I sort of drew breath and I said, that's great news. Your ophthalmologist obviously predicts that you're going to be still alive in 6 years' time. It's really funny because he hasn't called me or been returning my calls since. But I want to make a real prediction now, a serious prediction. Picture Sydney on a cold winter's Saturday afternoon. Imagine tens of thousands of people gathered on Bondi Beach. They're all rugged up against the cold and there's going to be an air of excitement. I can tell you right now that 4 times while those people are gathered there, they're going to emit a cheer and a whoop at precisely predictable intervals. The loudest cheer is going to occur at just before 2 o'clock in the afternoon. And you know how easy it is to distinguish the cheers of a crowd at a football grand final compared to those people at a soccer match. They sound totally different. Well, this crowd will have their own unique sound based on my observations and experience anyway. But I'll come back to that. First of all, what I want to do is take you on a short journey that will leave you in no doubt that physicists have the ability to predict the future with extraordinary accuracy, and that the consequences of that are the foundations of modern civilization, and possibly its destruction, but I'll try and maintain a positive outlook tonight. There's an oft-quoted aphorism that says it's difficult to make predictions, especially about the future. Well, physicists can predict the future, in contrast to the likes of astrologers and clairvoyants. I was entertained to recently read that a multi-million-dollar art heist in Brazil had been connected to the, quote, bogus predictions of a phony clairvoyant. And I can only assume that the other type, any of whom I've failed to ever meet, are the genuine clairvoyants. There's no shortage of people that claim to be able to predict the future, and usually not without first extracting money from people less well informed than the audience here tonight. Phonies aside, history and technology especially is littered with poor predictions, of which you're probably familiar with most of them. In 1828, a professor at University College London said rail travel at high speed is impossible because the passengers unable to breathe would die of asphyxia. In the early 1940s, famously, the IBM president at the time said, I foresee a time when there'll be a need for maybe 5 computers in the world. True. 50 years ago, my father, he was a farmer, and he used to often say, if I really want to know what the weather's going to do, I just go outside and look. Well, how things have changed. When I pull out my phone and look at the weather app, and it predicts that after a run of 5 or 6 days of sunshine coming up, it's going to rain cats and dogs. Usually it does. How things have changed in that 50 years. However, drilling deeper into the weather app sometimes leaves me perplexed when it informs me that there's going to be a 70% chance of between 5 and 20 millimetres of rain between 10 and 11 a.m. Well, what does that mean? Is there a 70% chance of some rain falling between 10 and 11? Can I expect that there will be up to 70% of 20 millimetres falling? Is there a 30% chance that it will fall outside of that time? What would I do if it were rather 65%? I've got no idea how that information is going to improve the quality of my life, but I usually just throw in a folding umbrella to be sure. An intelligent pub audience like you knows the difference between weather and climate, of course. Climatologists, when it comes to predicting the future, take the easy way out. In fact, they predict the past. It sounds crazy, but one way to test a climate model is to take the data from 100 years ago and plug it into the climate model 50 years ago, and if it compares well to the climate records from 50 years ago, then things are looking good and maybe the model will be useful in predicting the future climate changes. You know, lasers were predicted by Einstein over 100 years ago. The inventor of the first laser, the famous ruby laser, said, I think the laser is really a solution seeking a problem. Never could he have imagined or predicted that there would be today barcode scanners, digital information storage, surgical devices measuring the distance of the moon with an accuracy of 3 centimetres, surveying weapons, cutting, welding, printers, tattoo removal, cooling atoms to almost absolute zero, and optical fibre communication. All of which depend on lasers. Let's talk about gravity. When I was a teacher, there was a lovely lady called Mary, the salt of the earth type of person that used to clean my labs at the school where I worked. And early one morning, she stopped me in the corridor beside a poster of the solar system. You know, every school has a poster of the solar system, and usually several out-of-date posters of the periodic table as well, most of which have argon on them, as it turns out, Phil. And she inquired earnestly, is it true that the Earth goes around the sun? I was somewhat taken aback by such a question that such a question could be asked in the 21st century. But then I took time to reflect on the fact that when Copernicus first published the sun-centered model of the solar system, it didn't really catch on, and it wasn't an immediate hit because its predictions were hardly any better than the predictions that could be made using Ptolemy's Earth-centered model of the solar system. Plus, it really got the Catholic Church offside, and that's another story. Halley's Comet was observed in 1682, and it returned again 76 years later, just as Newton's gravity had predicted. And it's done so ever since, every 76 years. I'm glad you did the little experiment dropping the bottles, because I want to talk briefly about that just for a moment. At school, you encountered a formula that would have allowed you to predict the velocity at which that bottle hit the ground. However, the formula that you learned was misleading and flawed. It takes less than 5 seconds for the predictions to go wrong with something like the bottle, because it doesn't take into account air resistance. Not only that, but it also assumes that the Earth is flat, and not only that, it assumes that the Earth's gravitational field is uniform, and neither is true. It's also based on Newton's law of gravity, which we now know to be incorrect. Nevertheless, Newton's theory of gravity can be used and applied to send spacecraft successfully throughout the solar system, as we all know. Getting a spacecraft to Mars is actually pretty easy. You just send it outwards in the solar system, aim it at a point. Well, you set it on a path where its orbit around the Sun will intersect the path of Mars in 7 months' time. Simple. It's been done lots and lots of times. But on the other hand, getting a spacecraft to Mercury is a totally different kettle of fish. Right now, there's a spacecraft heading to Mercury. It was launched in 2018. It'll take 6 years to complete its journey to go into orbit around Mercury. During that time, it'll orbit the Sun 18 times. It will come gravitationally close. It'll have a gravitational close encounter with Earth. It's already done that twice. Venus and Mercury itself, and it will do that 10 times in order to slow down enough to be captured by Mercury's gravity. That, as you can imagine, takes a lot of accurate predictions. The James Webb Telescope orbits the Sun in exactly 1 year. It's been in the news a lot lately and producing absolutely fantastic photos. Thanks to the combined effect of the gravity of the Earth and the Sun, it takes exactly 1 year to go around the Sun, even though it's further from the Sun than what the Earth is. In addition to that, it simultaneously orbits around a point 1.5 million kilometres away from the Earth called L2, and it does that once every 6 months, as well as going around the Sun every year. Newton could have predicted all of that, though, with his theory of gravity. However, all was not well with Newton's very successful theory of gravity. In 1859, it was noticed that the orbit of Mercury was not quite consistent with the predictions made by Newton's law of gravity. And in fact, Newton had to be wrong. It wasn't until 1915 that Einstein proposed his general theory of relativity, which was not only consistent with Mercury's motion, but predicted exactly why it should happen. Einstein's theory of gravity was further confirmed in 1919 during a solar eclipse, spoiler alert, which measured the bending of light from distant stars by the Sun's gravity. Newton also predicted this effect. But because his theory was wrong, his prediction was 50% less than Einstein's correct prediction. Einstein's general theory of relativity predicted black holes and gravitational waves. Both have been observed this century. In fact, one was the subject of a Nobel Prize not so long ago. In 1931, Paul Dirac, just using pure mathematics, predicted the existence of the positron, which has been used to make fantastic medical images. I've alluded to weather apps on our phones, and the mobile phones that we all have in our pockets are dependent upon the predictions made by quantum physics and a whole lot of other things like James Clerk Maxwell's prediction of electromagnetic waves and a whole lot of other components which dependent on strong physics predictions, including the circuits, microphones, speakers, cameras, sensors, and so on. So I just want to return to the Bondi Beach prediction, which I started with near the beginning. The loudest cheer is actually going to occur at 19 seconds before 2 p.m. on that Saturday afternoon. The events of that day won't be confined to Bondi Beach. There'll be similar huge crowds gathered at the Opera House and other vantage points across Sydney, as well as out in the west, in Mudgee, in Dubbo, and in Bourke. I'm talking about the total eclipse of the Sun, which will be visible within a 100-kilometre wide band across the country from the Kimberley to Bondi on the 22nd of July 2028, not so far away. People in Bourke will actually observe the eclipse 18 seconds longer than the people in Bondi, so go west, young man. And the people in Bondi will see the beginning of the darkness as the sky blackens 9.5 minutes after the people in Bourke see that happen. By the way, there's going to be chaos on the roads on that day, just like there is tonight in Sydney. Probably much worse. There'll be hundreds of thousands of bits of eclipse memorabilia sold, but just bear in mind it will all be cheaper on the 23rd, the day after the eclipse. Let me just conclude by saying that physics is about predicting the future. Sometimes the practical applications of physicists' predictions are not immediately obvious. Einstein did not predict GPS navigation when he developed his theory of relativity. When the seeds of quantum mechanics were germinating at the beginning of the 20th century, no one predicted its application to semiconductors, lasers, solar panels, and communication using optical fibres. These applications, I think you would all agree, are foundations of the 21st century society, and they underscore the need to continue pure theoretical or pure physics research, because we can't tell the future applications of the things that some of our academics are working on right now. And by the way, if you're thinking of going to Western Australia, to Exmouth, to see the eclipse next year in April, just bear in mind that all of the accommodation in that town has been booked out for several months already. So good luck. Thank you, guys.
Greg Pitt, thank you so much. I predict that there's going to be another round of applause for Greg. I also predict that I'm going to be buying a lot of drinks for Imogen after this show. All right, moving right along to another amazing individual who I've known for a long, long time, but I never knew that he could talk without slides. What a talent. John August.
Okay, so I hope that's all going all right. Excellent. So I've had a long time interest in the Industrial Revolution, and today I'm going to recite a testimony from the 1870s. Now that's located in the UK and not Australia, but I will be closing off with some recollections of an eclipse I saw in South Australia all that time ago. But anyway, the Industrial Revolution, some might say the 1870s, that's not really the Industrial Revolution, that's actually the age of sulfuric acid. You know, I've sometimes wondered, maybe I could write a romance novel and call it Love in the Age of Sulfuric Acid. I wonder how well it would sell. But anyway, okay, so testimony from the 1870s. Yesterday, I went to see the factory just outside town. It's been there for a few years, but it was only then that I really understood its significance, its part in the new age around us. Its black smoke broadcasts to the world the productive energy inside, our part in the new technological age. The steam engine has replaced human toil, able to run continuously 24 hours a day, and steam trains crisscross our nation, developed from Stephenson's first innovative design in 1829. But it is symptomatic of many different advances. We can build even taller and larger bridges and buildings. And in London, a decade or so ago, they built the Crystal Palace to house the Great Exhibition, a grand construction of iron and over 1 million feet of glass. It used trusses which represent the very latest advances in the processing and use of iron. It includes artificial climates to provide a haven for all manner of plants and animals from across the empire. Thomas Drummond has invented a source of light so incredibly bright that it can be used to simulate the sun in theatres. He directs a hydrogen flame onto limestone. It's finding use in lighthouses where it guides our ships home from the far reaches of the empire. But it is not only technology where there have been such innovations. In the abstract realm of mathematics, Dr. William Somerville has been gracious enough to support his wife Mary in translating and popularising Laplace's mechanism of the heavens. We can now analyse the orbit of the moon using an astronomical number of terms. Yeah, that's a bit of a pun. I'm sorry, I couldn't help myself there. But in any case, we can now appreciate details in its motion hitherto unknown. The moon's rotation is locked to the Earth, with the same side always facing it. But because the moon is not a perfect sphere, and its orbit not a perfect circle, it does wiggle ever so slightly as it goes through its orbit. And it is only through the perfection of this analytic telescope that we can appreciate details about the universe before our optical telescopes are able to. We recently won the Crimean War and demonstrated the empire's ability to reach across cultures and meet with the Ottoman Turks on common ground to defeat the Russians and others with their ridiculous claims upon the Holy Land. This conflict provided an ideal application for our best military minds and other recent advances in technology, including, in particular, the electrical telegraph. Florence Nightingale applied the methods of mathematics to understand mortality in battlefield hospitals, and we've been able to put those observations to good use. It shows the new spirit of the age, where we don't just use mathematics to understand bridges and buildings, but we nowadays apply mathematics to the very things that we do. These are examples of the great many things happening all around us. But closer to home, in the next town, they've set up a tannery. We see the march of technology all around us. I watch the billowing patterns in the black smoke, dynamic, alive, changing, pushed along by the wind. And I felt such pride that human energy, progress, and industry have not just advanced, but have reached our very own town. We live in a special time in history. We have seen such great things unleashed by human thought, creativity, and innovation, technology, appreciation of the world around us, the reach of the empire. You can feel it, you can taste it. It is a wonderful age we all live in, a time that you and I are privileged to be alive in. The future beckons. Truly, there are great things ahead. Okay, now on, thank you. Now, there was an activist, a scientifically inclined activist in the Sydney scene many years ago who went by the name of Predator. And he sadly passed away quite some time ago. And those of us that do remember him will all say the world is a lesser place for his absence. But you might wonder, why on earth would someone call and go along by the name of Predator? Well, people did actually discover a quote from the book, From Creation to Chaos, that perhaps sheds a bit of light on that, which I'll now recite. The search for truth is predatory. It is a literal hunt, a conquest. There is that exemplary instant in Book 4 of the Republic when Socrates and his companions in discourse corner an abstract truth. They halloo like hunters who have unearthed and run down their quarry. Even if enjoined from the scientific quest, somewhere at some moment, a man alone, a group of men addicted to the drug of absolute thought will be seeking to create organic tissue, to determine the nature of heredity, to produce the cloud chamber full of quarks, not for renown, not for the benefit of the human species, not in the name of social justice or profit, but because of a drive stronger than love, stronger even than hate. That is to be interested in something for its own enigmatic sake, because it is there. Okay, now. Okay, I was going to do my eclipse recital, but I guess not, I suppose. Well, that long. Will you let me? Go on. Do it well. Okay. Do it well. All right, here we go. All right, I saw an eclipse in 2002, the first I'd seen. Later in 2006, I was to travel to Turkey with the Sutherland Astronomical Society to see another eclipse. But I wrote down my impressions of the 2002 eclipse, which I'll now revisit. My first eclipse, some lucky Melbourneites saw one a number of years back. We went to Purple Downs, a site roughly midway between Woomera and Roxby Downs. This included a marked-off area, though many people settled outside it. There was a lower speed limit for the area, and the police booked one person while I was there. Others took photos of the event. With the help of eclipse shades, which we purchased at the Woomera Visitor Centre, we watched the slow mechanical progression of the eclipse as the moon cleaved off more and more of the sun. And we generated lots of images of it from straw hats and tried to pick up differences in the shadows cast by the eclipse. What surprised me was how long it took for the light levels to visibly diminish. This probably only took place when the sun was about 95% obscured. I guess the sun gives out so much light that even a fraction of it still illuminates. And then, totality itself. Wow, pictures do not do it justice. The corona sits there and glows. It's alive, and to sit there in the sky with the surrounding landscape around you. Wow. And even that light is a bit bluish, like a xenon light, quite different to the, I guess, yellowish light we're used to from the sun. It's obviously something different happening there. Now, people didn't whoop or swear, as a British astronomer suggested would happen. Just an occasional spoken wow or gee, but nothing dramatic. It was impressive, though I certainly would not travel halfway around the world, as some international visitors had, to see a 30-odd second eclipse, maybe for a 3-minute eclipse. But this was, by strange coincidence, here in Australia. By further coincidence, I was able to see it from Woomera, a spot reasonably convenient and familiar. But the eclipse in its own way respects no boundaries. The Earth becomes a celestial object, sweeping its way through the solar system in accordance with Kepler's laws, more than just a world spotted with continents. The Earth is reduced to its mathematical foundations, wherever the Sun, Moon and Earth in their orbital positions. We have latitudes, longitudes and points on the celestial sphere. And that is what an eclipse reminds us, that we inhabit a planet. So one last closing thought. We are born of stars. We can reach them again.
John August. All right, we are going to shortly take a break and wrestle with the TV. I just want to make a short comment about the moon being locked in by tidal forces in orbit. So the moon always faces the Earth, right? So if you are on the moon, the Earth does not go around, right? Because the Earth rotates and the moon rotates at a different rate, we see the moon travelling, right? But it lags behind the sun, right? At 28 days, the moon moves around. But if you're on the moon looking at the Earth is in the same place all the time. And eventually, the Earth is going to lock to the moon as well. Over thousands and thousands, millions of years, the tidal forces are going to lock them together. And imagine that. The moon's going to keep slowing down and stop right over Sydney. And people from LA, they won't be able to see the moon ever. They'll have to come to Australia just to see the moon. How cool is that? So there you go. There's a future to look forward. There's another prediction from physics. I'd like to give a big thank you to our 3 presenters who've jumped up. They're all meant to be later in the show on a quick whim.
Hello again. Let's try this for round 2.
Yep.
So as I was saying, I study at UTS and I'm part of the Quantum Materials and Nanophotonics group. And with that, we look at the quantum materials, the quantum properties of materials, and essentially small light, and how it behaves on a small scale. So I'm talking about quantum light sources, also known as single-photon emitters. And the reason we're looking at that is it's quite fundamental research for a lot of quantum applications, including communications, QKD, information, and sensing. So the image on the right is an example of the sensing. I want to talk about more how it works, because that's cool. This is just other stuff that other people do. So I think a lot of you are a lot more qualified than I leveled this presentation for, but my family is here, so we're keeping it simple.
Give it up for the Spencers!
So one of the words you hear get thrown around a lot is quantum. And like, it's used in movies, it's used in, I've heard people describe it as big, as new, and it's a lot of things, right? It's a change in the way we think. There's some phenomenon that cannot be explained classically. The main concept I want you to keep in mind for this presentation is going to be quantization. And I'm going to give you a little analogy to help with that. So the analogy I want to use is the concept of a hill. If you're walking up a hill, you can step wherever you like. If you're rolling a ball down a hill and someone takes a photo, it could be anywhere on that hill. The quantized version of that is like steps. Walking up the hill, you can only be on step 1, step 2, step 3. You can't be on half a step. Same with the ball going down. I know you can see it moving between, but we're going to pretend you can't, and it can only land on each step. So that's the idea of quantization that I want you to keep in mind in terms of our quantum tonight. Then we're going to talk about light sources, because we're doing quantum light. And we've got light sources more traditional, like fire or halogen lighting, and that's incandescent lighting, meaning it's just produced from heating. In newer technologies, we've also got light-emitting diodes, and we get light coming from this recombination of electrons and holes, which is all awesome. But something all this has in common is you get a bunch of light out. What we want to do for those quantum applications that I skimmed over at the beginning, because that's not as interesting as what I do, is look at one piece of light at a time. So putting those together, we've got our traditional view of light, a spectrum, it's all considered in waves, it's continuous, there's a lot of it. Then taking the quantized version of that, we're then looking at it as though it's particles. The smallest piece of light you can have is called a photon. So that's a single piece of light, or a quantized piece of light. And they will have different energies depending on color and stuff, but the smallest piece of light is a photon. And we want to look at one of those. Not a bunch of those in all those other ways we talked about, but just one at a time. And this is where I think it gets cool. Or not? So, how do we do that? We know from the LEDs that electrons can emit light. We know from the photoelectric effect, which was Einstein's 1921 Nobel Prize, that electrons absorb light. And it's just a transfer of energy like everything else we consider in the physics world. Oh. So what we want to do is we want to have a single electron, and we want to give it some energy. And we can do that from the photoelectric effect by giving it light. And we give it energy, and it absorbs that energy and moves to a... It's supposed to move.
It's coming. There we go.
No, the electron moves up, Phil. It's not moving. Just pretend the electron moved up. It moved up, it absorbed this energy, it's in a high energy state. But as I'm sure, well, at least I can relate to, is I can't last in a high energy state very long. And just like me, the electron wants to relax. Well, that's sad. Maybe it's just me, maybe someone else needs to go. Anyway, from that diagram, when the electron relaxes, it needs to emit that energy, and it does that by releasing that energy as light, which is a photon.
Great recovery from Imogen Brown on the left wing.
Thank you, Imogen. Excuse my typo in the equation, but when the electron comes back down, a photon gets emitted, and it's of a particular wavelength or energy, and they're essentially interchangeable as per that equation. So if we have an electron and we can control the energy levels it can exist at, because remember from that quantized view it can only exist in certain levels, we can control the piece of light coming out, and we can just look at one of them at a time. But of course, we can't just walk down the street and grab an electron and be like, oh, let's take this to the lab and look at that, because there's so much going on around it. That most people like there's nothing around us, but on an electron scale, there's heaps. So we can't do that. So what we do is we look at crystalline structures. So with a electronic property called a wide bandgap semiconductor. So these crystals, essentially, it means that electrons can't flow in these crystals. Then what we can do is create an atomic defect. So in this case, this is a material we work with. It's called HBN, hexagonal boron nitride. And you have alternating borons and nitrogens. And by knocking out a boron atom, we create this environment where there's this single electron, and it has nowhere to go. It cannot go anywhere. So it is isolated how we want it to be able to study it. And then we can do what we were talking about on the last slide, and we can give it energy, but it can't escape anywhere. So it just absorbs that energy to a certain level, and then releases that, emitting a photon, and repeating that cycle. Oh no. Okay, my animations aren't gonna work. It all moves. I was really proud of myself. But, oh well. And as long as we're giving it energy, it can repeat that cycle of getting excited into a higher energy state, relaxing back down to its ideal energy level, and emitting a photon. And that's the mechanism that our whole group works around. So I personally work in fabrication. So I make devices that work with these. Ritika, who's going to talk to you next, she's going to build on this and actually talk about her research. But this is the fundamental concept that our research is built around, and I think that's pretty cool. So thank you for listening. I hope...
Standing ovation, standing ovation.
I'm glad we got there.
Ritika!
This is a long night. Okay, before I start, thank you everyone for coming here, listening to some physics people on Friday night. I know it can be hard. Okay. So I'm Ritika, I'm a second year PhD student doing my research under supervision of Igor and Milosh at UTS. And just like Lesley, I'm also part of TMOS. So, Lesley must have talked to you about single-photon emitters. So my research is based on growing those single-photon emitters. Some of the applications that we have are in quantum computing and quantum cryptography. So what these applications allow us to do is, or will allow us to do in future, is communicate and share information online in much safer way, and also do some complex calculations and simulations for the future work. So what are single photon emitters? They're, think of them as Nerf guns. So just how when we play with Nerf guns, you shoot one bullet at a time. So single photon emitters are high pulses which emit one photon at a time. So some of the properties that we want with single photon emitters, which will allow us to use them in some applications, are brightness and photostability. So photostability in this case is when we do the measurements or use them in applications, we don't want them to blink, and we want brighter emitters, which means we want them to emit photons at higher rate. We can also call them defects, and why can we call them defects is what I'll explain in a minute. All right. So now that I've talked to you about single photon emitters and all those applications, how do we make them? So it's just something to so all of you, I don't know all of you, but like my best friend back there, she loves knitting, so I wanted to use this as an example. So just like in knitting, while you're knitting, you want to repeat the patterns, right? So hexagonal boron nitride is the material that I use to host these single photon emitters, which they're structures of boron and nitrogen atoms bonded together to form this hexagonal structure or lattice. And do we want these continuous patterns or perfect lattice? No, this is not useful for us in the applications. So we don't want that. So the cross is supposed to come now. So what we want is missing atoms. We want missing atoms from the lattice, and we call them boron or nitrogen vacancies. So I'm not going to go in much detail about these defects because that would need 10 more slides. So as you can see, these blue circles here are nitrogen atoms, and the pink ones are boron atoms. So a missing nitrogen atom shows you a nitrogen vacancy, and over there in the right-hand side, there's a nitrogen vacancy, but an extra boron atom. So how do we make them? Just like I said, with knitting, I don't need threads. Okay, I don't use threads and needles, but what we do is we use a heating chamber, and chuck the sample in, add some precursor or the chemical, and we just grow them. I wish it was that simple. But it is a bit complicated. We get it done, otherwise no PhD. So what we have here is 2 pressure gauges, a chamber in the middle to heat the sample, and most of the process is simple, but it just takes 2 days, and sometimes it doesn't work. You can't tell until the 3rd day when you do the measurement, if you get the booking done in time. So this method is called low pressure CVD, and I'm not going to bore you with the details of the experiment. Okay. Does it always work? No. I was excited for this part. But to see if the experiments have worked, we do set of measurements. To say that we have HPN, we do some Raman and peak analysis. Then we do single photon emitter measurement that Lesley would have gone through with you. And these are some other cool experiments. So with my work, we've done the HPN growth on several different substrates, metals and dielectrics, and other sorts of different experiments with the growing on different plasmonic structures, etc. So the future of the work is we can use them on different plasmonic structures to be used in various applications in the quantum field. It helps us in miniaturizing the computing and other sorts of technologies we use nowadays. So coming back from big computers to laptops to iPads and iPhones, we want to take it to nanoscale. And the next one is, based on my research, the next step would be looking at doping, which would allow us to study these emitters in detail and get better results and better devices. And finally, it will allow us to work with all those quantum applications I talked to you about in the beginning. Thank you. Thank you for the team to help us making it work. Thank you.
Ritika! How many molecules in a tub of guacamole? There's number. Okay, my name is Dr. Simon Crook. I work for Crooked Science. I work with primary schools and high schools all over New South Wales and around the place. Advocate a lot for teachers and everything. No one is lying to children in schools. There's a few misconceptions out there, and then there are age-appropriate models that we teach as we go through the ages. I just... anyway, okay. We are going to do a quiz. We're going to use something called Kahoots if the technology works, and if it doesn't work, I'm going to shout out questions, which is interesting because some of these require some images which I'll have to describe, so we'll see how we go. So we'll kill 30 seconds whilst people get their mobile phones out and go to Kahoot. That's K-A-H. Phil says you can now turn it on. Phil says it's on him. It's on his head. So we'll try it. It's all right. There is a plan B. Oh, things are working so far. So if you go to kahoot.it, thank you, Italy. And when it asks for a name, when I'm with kids, it has to be a clean name. We are in a pub. Knock yourselves out. In the way this one's set up? Really? I must have the child-proof settings on. I apologize. Oh, we got, okay, yeah, random stuff. Okay, it gets interesting, as you can imagine, with teenagers when they choose names. Anyway, you've got your game pin, so people are getting in. Fantastic. Do you know which random animal you are, or are you left guessing? Okay. The resolution's going to be interesting on the first question when we get there. So we'll just let people log in. Hands up if you've logged in to the quiz. And hands up if you're still trying. We'll give you a moment longer. Okay, the way this works, for those of you who haven't done a Kahoot before, a question is going to appear. Then the 4 options, it's multiple choice, are going to appear. They are color and shape coded, as in, it's like actually, I think it's just color, like a blue diamond, a red diamond, whatever. Those colors appear on your mobile device. You choose the answer you want on your device, and it records your response. Who's still trying to log in? All right, we'll give you, yeah, look, you've waited for us, we'll wait for you. Whilst we're waiting, what do you call a tooth in 1 liter of water? A 1 molar solution. What's brown and sticky? A stick. All right. Can we? Anyone still fighting? Logging in? Kahoot. Right. Let's get a move on. Can we press start, please? Image in. First question. What actually goes on? Oh, sorry. That's the name of this thing. Okay. What was I attempting to draw in front of 17 and 18-year-olds here? Last year, this time last year, in fact, revision, leading into the HSC. What was I attempting to draw? Yes, it was Thomson's apparatus. Any high school science teachers will know about test tubes and rockets and cock-shaped cathode ray tubes and, sorry. Awesome. Can we click next at the top, please, Imogen? And who's Magic Rooster? Do you know who you are? Oh, fantastic. You're in the lead. There's 9 questions to go. And the next one, please, Imogen. Okay. Answer this HSC question. It's a little bit small, I think, on the screen. I'll read it out. You've basically got a magnetic field in the plane of the screen. You've got a metal rod rotating in the plane of the screen. You're measuring the EMF between P and Q. What is the trace against time? This was 2 years ago. The writer, or the chief examiner, is in the room here, which is fantastic. And the answer is C, a null result. We don't get enough null results out there because it's all orthogonal. If the EMF was measured in and out of the screen, then we would measure it, not in the plane. Come on, guys. 10% of the states got that right. If we randomized, if we gave it to a bunch of chimps, 25% of the state would have got it right. When you look at the profile, your band 6s did better than the band 5s, 4s, 3s, 2s, and then the band 2s did well, okay, relatively. All right, next question. In 2021, what percentage of students achieved an HSC mark of 50 or above? In physics. This is physics, sorry. This is about physics. I'm so sorry, because that would really change your answer. So, a little explanation here. The students do their exams, and then their exam marks get moderated, and that means that 98.25% get a score above 50 because it's more palatable to parents. Okay? So a score of 50 is actually a band 2. Which is going to be interesting with the next question. Oh, actually, we need to see where the scoreboard is. It's lagging. That's okay. That's okay. So if anyone's interested in how can that be and what's it all about, there's an article in the AARE that was published last year you may wish to read. And there's also another article this year. Oh, there we go. Who's Radiant Deer? Oh, there you go. Oh, right. So we've got the two leaders there, highly competitive, just fantastic. And, oh, we had 3 people shoot up. All right, next question. In 2019, what raw exam mark was required to achieve band 6 in HSC Physics? I did include the subject this time. Ooh. That's the right response. Ooh, is it? Okay, 76. So band 6, for those of you know who read... Does anyone here work for the SMH? Okay, we don't have all night here, but if anyone works for the SMH, shame on you for perpetuating the totally weaponized thing that is education in New South Wales. Because a band 6 is reported as 90. If you've got any children in the teens doing their bands, HSC, it's 90. They didn't get 90. Well, in physics they didn't, and in chemistry they didn't, and so on. There might have been some other subjects that remain nameless. They might have got more. But here's the irony. Okay, only 10% of people manage to get band 6 because physics is hard. So when they get the honor roll in the SMH of all those kids who got band 6s in all their subjects, guess what? There's no physics or hardly any physics or chemistry teachers. Even with all the selective schools having a bazillion physics and chemistry classes, it's stacked against them. Okay, and then people get patted on the back in other subjects, and physics teachers think, bollocks to this, I'm going to leave the profession because I'm swimming against the tides. There's a bit of emotion here, it's a bit pent up. Okay, and then, no, but in all seriousness, then physics teachers and coordinators and even principals then get hauled over to the coals. Why aren't your physics results the same as visual arts? Because 2 years ago, a band 1, a fail in physics, contributed more to ATAR than a low band 4 in visual arts. You can read this in the AARE. There was an article last year and there's an article this year. Okay. Oh, radiant deer. There we go. Sorry, the important stuff. I'm getting a bit too emotional here. Next one. It's going to cheer up in a minute, honestly. In an SMH, God love them. Okay, what percentage of schools reported a shortage of physics teachers? This was, what, last month? %, yeah, going to the extremes. That tricks you there. Yes, that bodes well. You know, Australia, STEM, all the rest of it. If you do physics, you have choices. Why be a physics teacher and put it with all the crap you're reading about in the press when you can do other things with your lives? There's a big shortage out there. And just before we advance, that article was talking about independent schools. So chuck in non-selective government schools. If you're in the Mount Druitt area, I think there's 6 schools there. One of them has a physics teacher, period. I know of one independent school that has 8 physics teachers in one school. We've got ever-increasing social inequity, and if we don't do something, it's just going to get worse. Sorry for being political. Next one. In which grade do students first learn about algorithms? This is broader than HSC physics. This is New South Wales curriculum. Kindergarten. Awesome job. So when the new primary school science syllabus came out in 2017, imagine all the kindy teachers when they got to read about algorithms. Yeah, they got to, anyway. Just the actual secret. They don't have to start coding and things, but some interesting terminology that's thrown in there. We're starting them early. Inspired wombats. Oh, awesome job. Okay, next question. I'll push on. In support materials for teachers created by the Australian Academy of Science, anyone here from the AAS? Which grade has this background reading? Water molecules are polarized. This means they have small positive charge at one end and a small negative charge at the other end. That was in a 146-page PDF for teachers for background reading in preparation for teaching Year 2. Because Year 2 needs to know about polarized molecules, not that a water molecule looks like Mickey Mouse's head. That's water in Year 2, please, people. Sorry, AAS. You also had mistakes in your whole sundial instruments. Anyway, next question. In HSC, Earth and Environmental Science syllabus, how many times does the phrase climate change appear? Ooh. Zero, absolutely bugger all. Because they weren't allowed to. They weren't allowed to. This is weaponized. This is politicized. They weren't allowed to. It's called climate deviation because that's on everyone's tip of the tongue. They weren't allowed to. It's in the 7 to 10 syllabus, but that's about to get changed. Depending on what government's in power when that's changed, who knows if it'll be in the next 7 to 10 syllabus. There we go. Who knew education was so fraught? Next. Will someone think of the children? Who are this motley crew? Okay, I'll describe the picture. You had Derek Muller standing in the center, holding an awards. And you had Christine Lindstrom from UNSW. And you had Helen Georgiou. Oh, there you go. Oh. Okay. So super, Sydney University Physics Education Research Group. That's our research group, and there's not much physics education research out there. I think there's us and UNSW. We're very small, we're very niche. Please support any physics education research out there. Hopefully by this evening you might understand there's a bit of a need, not least politically, but also it also helps about how to learn to teach in the classroom. Magic Rooster, where's Magic Rooster? Awesome. I think this is the last question. Who wrote Einstein was wrong, not your science teacher? Yeah. Was it Geraint Lewis and Luke Barnes? Was it Magdalena Kirsting and David Blair? Was it Leonard? Was it Crook, Loyan and Gordon? Yeah. It was in the conversation last year. You can read it. It's about age-appropriate models as we go through sophistication in learning along the way. Sorry, it's shameless self-promotion. And the podium in 3rd place. Inspired Wombats. Congratulations. 2nd, Brave Pelican. Where's Brave Pelican? Oh, coming. And in 1st place, Magic Rooster. Happy days.
Coming up, it's the end of Science Week, but coming up is the Sydney Fringe, and there is some great science content in that. Rachel's show is one of them, A Flying Photon. Stir-Fried Science by Dramatis Scientificae at the same place, at the Newtown School of Performing Arts. That is a show that I've been part of, I've written much of, but I actually won't be performing in these performances, but still a great show if you want to know all about fusion and Clive Palmier, that's the French guy, and Australia's climate targets and those kind of stuff. Go along and see that. And I will also be at Macquarie Open Night. There is a pub section to Macquarie Open Night. There's Rachel. Hey! Click it forward, click it forward. No. Nope, it's gone. All right. We're back to the ocean. Anyway, so the way this song works, this is my hymn slot, all right? The congregation is called upon to contribute. So repeat after me. Oh, when the saints go marching in. Oh, when the saints go marching in. Beautiful. All right? Everything I say, you repeat it. Well done to the pedants in the room. That's a bit more like it. Oh, when the science gets peer-reviewed. Oh, when the science gets peer-reviewed. Oh, when the science gets peer-reviewed. Oh, I want to be in that journal when the science gets peer-reviewed. Oh, when the grants get handed out. Oh, when the grants get handed out. Oh, I want to be in that number 18%. Ooh. When the grants get handed out. Oh, I forgot to ask, who's the VC of Sydney Uni these days? Nobody knows. New South Wales? UTS? Okay, let's just use those VCs. Oh, when those VCs sign up their profs. Oh, those VCs sign up their profs. Oh, I want to be on that payroll when the VCs sign up their profs. When Fred Nobel gives out those gongs. When Fred Nobel gives out those gongs. Oh, I want a Nobel Prize. You know I deserve it. When, it's actually King Carl. When King Carl gives out those gongs. Oh, when the grants get handed out. Oh, when the science gets peer-reviewed. Thank you, ladies and gentlemen, and everybody who's wearing purple as well. It's been wonderful having you here. Thank you for putting up with our amazing technical challenges, and a big round of applause for Imogen Brown. Thank you so much to Harold Park for having us. Thank you so much for all our presenters, and we will see you next year. Thank you very much.